Okay, so this section is 7.3 of our finite notes, and the title is Probability Problems Using the Counting Techniques. And these would be the counting techniques that we actually use from Chapter 6. So we'll be using those to find probabilities. So at the top of your notes, students should be able to find the probability of events using counting techniques. Lots of just story problems today, a lot of applications of finding probabilities. So here we go. Number 1, a cooler contains 7 cans of cola, 4 are regular colas, and 3 are diet colas. If 3 cans of cola are selected at random, what is the probability that all 3 are diet colas? So what I'm thinking, and sometimes it helps to write this out, I need 3, I need my pen. I need 3 regulars all over the total number of cans in the cooler. So first of all, I'm going to figure out how many cans are in my cooler. 7. Let's figure out that total. That total is, okay, does it matter in the order that I select the cans of soda out of the cooler? And nobody's here to answer my question, so I'll answer it myself. The answer is no, the order does not matter. So I'm going to be doing a combination of 7, choose 3. Now in the numerator, I look and I need 3 regular sodas or colas out of the cooler. How many regular colas do I have to choose from? Well, I have 4, and I need to pick all 3 of those. Okay, so to save time, I'm just going to go ahead and give you the answers for these fractions. I'm not going to take the time to figure these all out, or we would be here forever. I would be boring you to tears. Combination 4, choose 3 is 4, and combination 7, choose 3 is 35. So that would be the probability that all 3 are regular colas. Number 2, in the situation in problem number 1, what is the probability that 2 are regular and 1 is diet? So I need 2, first of all, my total did not change. Still combination 7, choose 3. So the numerator, I need 2 regular colas. So order doesn't matter, it's still combinations. I have 4 regular colas to choose from. I'm picking 2, and means I'm going to multiply. And then I have 1 diet soda. So I have a combination of 3 diets to choose from. I'm picking 1. Okay. I know that 4 choose 2 happens to be 6. 3 choose 1 is 3. And then this we found out was 35. So I get 18 over 35 as my answer for number 2. So as you can see here, we've got it's not just picking one coin or one soda. We're picking different types. So we have to throw in our counting techniques that we used from chapter 6. That's what it's all about. Number 3, a box contains 15 CDs, of which 6 are scratched. All CDs have equal probability of being chosen. You pick 3 CDs at random to take with you to the car. What's the probability that are all 3 scratched? Well, first of all, how many total CDs do I have? Let's figure out our total sample space. Well, that would be in the denominator. I have 15 CDs and I'm going to pick 3. Order does not matter. Combination 15, choose 3. In the numerator, what is the probability that all 3 are scratched? So how many are scratched? 6 of them. So I have a combination of 6 of those, and I'm picking 3. Okay? So think about that. If you have to slow me down, you can always hit pause if you need to sit and kind of think about it for a minute. When I worked this out, I got 20 in the numerator and I got 455 in the denominator. Again, if you have to work these out, you do not have to reduce it all. You can leave it like that, or if it bothers you, you can change it to 4 over 91, but don't spend time reducing. Part B, what is the probability that exactly 2 are scratched? All right, so that means of my 6 that are scratched, I'm going to pick 2 of those. And then I have to pick 3 total. So of my non-scratched ones, 15 minus 6 is 9. Of those 9, I'm going to pick 1 of those, all divided by, once again, my total, 15, choose 3. So I get a final answer of 135 over 455 on that. Part C. What is the probability that at least 2 are scratched? That means 2 or 3 are being scratched. So I would be looking at this and saying, well, didn't I just do those? I have 2 or 3 being scratched. Don't redo the work. We just did it in part A and part B. So I'm going to take my 20 over 455, add that to my 135 over 455 to get 155 over 455. Okay, that's a 155. That doesn't look like a 1 there. Very good. Let me erase that. 155 all over 455. There it is. Okay. Number 4. A fair coin is flipped 4 times. What is the probability that both heads and tails occur? Well, that means I'm only flipping it 4 times. You can either really concentrate on either heads occurring or tails occurring. So as long as you have 1, 2, or 3 heads, that means the other coins would be tails. So I can think of it of this as, oh, wait a minute. My denominator is not going to be a combination like the last problem. I flip a coin every time. I'm thinking about the sample space. I have heads or tails every time, so there's 2 opportunities or 2 possibilities, and I'm flipping the coin 4 times. Flipping the coin 4 times. Wow, I need to slow down. So that means that my denominator, my sample space, is 2 to the 4th. Now in the numerator, I want both heads and tails to occur, so I could do, let's concentrate on getting tails, so that would just be a combination of 4 of the flips. I want 1 tail to occur, or of the 4 flips, I want 2 tails to occur, or of the 4 flips, I want 3 tails to occur. So I can do that problem like that. Okay. So in the numerator, I get, I don't know, you can work this out and reduce it. I get 7/8 as my reduced answer. Now you can also think of it as another option. I don't know how many people would think about this, but another option would be 1 minus what you don't want. So 1 minus what I don't want to have. Okay, it's kind of like what we did, total minus what we don't want. Now we can do 1 minus what we don't want. So I don't want to have all heads, and I don't want to have 0 heads or tails. It doesn't matter which one you think of it as. So a combination of 4, choose 4. So of the 4 flips, all 4 would be tails. And I also don't want 0 tails. So I can do it like that. Okay, either option will get the same answer. Okay, number 5. A student has errands at the bookstore, the bank, and the music store. The student makes a random choice of order. Ooh, there's an important word. Of the order in which to do the errands. Find the probability of each of the following. The bank is visited first. So if the bank is visited first, now, first of all, since it's telling me the order at which to do the errands, that's a big hint that we're going to be using permutations. Okay, if the bank goes first, that's one possibility. I have to pick it. And then I've got how many other errands to do. Of the 2, I'm going to order those. So these are permutations. Divided by permutation of 3 of them, I'm going to order them all together. Okay, so one more time, the bank has to be visited first, so that one visit, I only have one choice, permutation 1, choose 1. And then of the other 2, it's a permutation 2, choose 2, because I have to order those 2, divided by my sample space, permutation 3, choose 3. Okay, part B. Oh, this is coming up again. The bank is visited before the bookstore. We've talked about this a lot. Either the bank's going to go before the bookstore or the bookstore is going before the bank. So half the time the bank comes first, half the time the bookstore comes first. So the probability is just 1/2. Now you can think of it as probability times permutation of 3, choose 3 all over ordering your sample space. I don't know why I would continue to put in that permutation 3, choose 3 over 3, choose 3, because you get the same thing in the numerator denominator. So your probability is just 1/2. Okay, number 6. Suppose there are 3 U.S. sprinters among the 8 finalists in the 100-meter dash in the Olympics. If the 8 finalists are equally talented, find the probability of the U.S. sprinters finishing first, second, third. Well, if you think about that, equally talented, I got to come up with a denominator, my sample space. I have 8 finalists. So my sample space is putting my 8 runners in order. That is a permutation. 8 choosing, oh wait, I don't have to put all 8 in order. I have 8 finishing just first, second, third. Okay. Find the probability that the U.S. sprinters are going to finish first, second, and third. So I have my 8 finalists. I want to see how many ways could I order those in first, second, and third. So that would just be a permutation of 8 choosing 3. Now in the numerator, I have to say, okay, now I'm going to focus in on only the U.S. sprinters. Well, how many U.S. sprinters are there? There are 3, and I have to order them. So that would be a permutation of 3 choose 3, all the ways I can order my U.S. sprinters. And here is everyone. Okay, putting them in first, second, and third. So my answer is 6 over 336, and I can leave it like that. Or if you want to reduce it, 1 over 56, I do believe. Okay, the next one. A student selects 5 frozen dinners from 9 alternatives. The alternatives include 4 different pasta dinners, 3 different chicken dinners, and 2 different seafood dinners. If the selection is made at random, find the probability that at least 2 pasta dinners will be selected. At least 2 pasta dinners means I need 2 or 3 or 4. Is that the most I could get? That's the most I could get because that's all the pasta dinners that I have. Okay? At least 2 pasta dinners. So if I think about that, I'm going to do a combination of 4 choosing 2. If I have 2 pasta dinners, that means I have 3 non-pasta. So I'm going to group together the chicken and the seafood. So that would be 5 choosing 3. So did you notice what I did there? I just broke it down to just pasta dinners and non-pasta dinners. So that's why I can put the chicken and the seafood together. Or I can have a combination of the pasta dinners, choosing 3, and that means of the non-pasta dinners, that's a, what is that? I can't write. Okay, so back to this one. Combination of 5 choosing 2, or I can have combination 4 choose 4, combination 5 choose 1. Wow, that's a lot of work. That's just my numerator. That's just the number of ways I can get at least 2 pasta dinners. Now I have to divide it by my total sample space. How many frozen dinners were in that refrigerator? There are 9, and I'm picking 5. That's the number of ways I could pick everything there. And I would just leave it like that. Okay. Now, could we do 1 minus what we don't want? Yes, you could. If you think that would be less work, let me kind of write it out here. I don't have much room. I'm going to do 1 minus what I don't want, and that would be all 5 non-pasta dinners. Combination 5 choose 5. Or I could have just 1 pasta dinner. Oh, I don't have enough room to write it in there. So I'm going to squeeze it in here. That would be 1. That would be combination 4 choose 1, and that would be combination 5 choose 4. All divided by my total sample space, 9 choose 5. Okay, so, oh wait, that's not right. I put my division line. Oh, let's start again. Let me write it so I have more room. Here's method number 2. I could do 1 minus combination of non-pasta dinners, or I could have combination 1 pasta dinner and then 4 non-pasta, all divided by, notice the division line only goes underneath the second part, combination 9 choose 5. Okay, so that right there is combination 5 choose 4. Alrighty. So I'm going to try and fix that for a couple minutes while you get caught up. All right. So looking at number 8, The Student Union Board has 10 members. 7 are females, 3 are males, including Steve. 3 tasks are to be assigned, including that of reserving a room for meetings. The tasks are assigned at random and at most 1 person per task. Find the probability that Steve is given a task. So if I look at this, I'm just giving Steve a task. So basically, he's just 1 person, pick 1. And then everybody else, there are 10 members, so everybody else would be 9. I have to assign 2 more tasks, and they're going to be given, it didn't really say they're different tasks, so right now we're just going to keep that as a combination, 9 choose 2. And the denominator, my sample, would just be of how many ways I can assign task combination 10 choose 3. That means I'm not assigning the task, I'm actually picking the people to be given a task. Okay. Now, in part B, that's really kind of confusing. Go back and think about that again. 3 tasks are to be assigned, including that of reserving a room. So Steve is given a task. We just know that he's going to be included, and the other 2 are going to be given a task, and the denominator is just, I'm going to pick 3 people to be given a task. So I'm just collecting the people that are going to be assigned the task in part A. I have not assigned the task yet. Part B. Find the probability that Steve is asked to reserve a room. Okay, now we're getting into assigning a task. Now I'm going to switch over to permutations. Permutation 1, choose 1, and then the other 2 are being assigned a task as well, so that would be a permutation 9, choose 2, and my denominator would now be a permutation 10, choosing 3. Okay. Part C. Find the probability that both male and females are given a task. Okay, so there's a couple ways you can do that. I'll put them both up here. I can look at that since I just have 3 people. Of the 3 males, so it doesn't matter, I'm just picking the people to be given the task combinations. 3 choose 2 males and 1 female, so that would be a combination 7 choose 1. Or I could have 1 male and, so I multiply, 2 females, all divided by just picking the 3 people, 10 choosing 3. Okay, and that would be both males and females being selected. Now the other option, if you want to do 1 minus what you don't want to have all males, so that would be a combination of 3 choose 3. And you also do not want to have all females, combination 7 choose 3. I add those together and divide it by combination 10 choose 3. Notice I'm adding those because the negative is in front of the fraction, so whatever I get for that fraction, I'm going to subtract that from 1. Okay, number 9. Number 9, toss a pair of fair die 5 times. So then it asks, find the probability that the sum of the 8 appears 5 times. Well, first of all, I need to think about all the different ways I can get a sum of 8. So the sum is equal to 8. Maybe I shouldn't say sum is equal to 8. I should say sum of 8. Let's write those out. I can get a 2 and a 6, and a 6 and a 2. So I'm going back to that, flip back to the 7-1 notes where we have all the list of those samples there. And then I have 3, 5, and 5, 3, and I have 4, 4. I think those are all the ways that I could get an 8 that's on that chart. Well, how many ways is that? Well, that would be 5 out of 36. And I'm going to do this 5 times, and so I have the same probability every time I roll the die, the 2 die, so it's just going to be raised to the 5th power. All right, and that's all it is. I'd leave it like that. I don't know why I have a part A. I must have gotten rid of part B. Okay, number 10. What is the probability that a 4-digit extension number contains the number 6? What is the probability that a 4-digit extension number contains the number 6? Now the problem with this, it doesn't say if I have 4 6s, 3 6s, 2 6s, 1 6, and oh wow, this could go on forever. So what I'm going to do is I'm going to do 1 minus no 6s. Okay. Now think about your sample space. I could have the same number all 4 times. So that means how many digits do we have to choose from? 10. That's going to be raised to the 4th. When you have a repetition like that, you cannot use permutations or combinations. So now I'm thinking, well, what goes in that numerator? Well, that's going to be 1 minus. If I can't use a 6, that means I have 9 digits I can use. And I'm going to raise that to the 4th because I'm going to have the same number every time. So it's just going to be 1 minus the fraction 9 to the 4th divided by 10 to the 4th. There it is. Next page. I know I'm going quickly. I'm trying to get through this. If you need to slow me down or pause, just ask the sub to pause it so you can get caught up. Okay, this gets to the fun page. What is the probability that a 4-digit extension number has 1 or more repeated digits? Now again, this can get really complicated. You can have 1 repeated digit, 2 repeated digits. Is it going to repeat just twice or 3 times or 4 times? It gets really complicated. So I'm going to do 1 minus no repeats. That's what I'm going to do. In my sample space, again, it's a digit, so I can go 10 to the 4th. Those digits can repeat. So thinking about this, we have to think no repeats. That means I have to use a permutation or a combination. And since I'm doing a 4-digit extension, the order does matter. So I'm going to do a permutation. I have 10 digits, choosing 4. And there it is set up. Okay. The next one, it says 6 letters with repetition allowed are selected from the alphabet to form a word in quotes, meaning it could be a real or non-existent word. What is the probability that no letter is repeated? So if I want 6 letters with repetition allowed are selected from the alphabet, to form a word, what is the probability that no letter is repeated? Well, first of all, if you're picking letters to make a word, you can have repeats. So I have 26 opportunities every time I pick a letter, and that would be raised to the 6th power as my total sample space. But I want to narrow it down with no repetition being allowed, so that means I have to be using a permutation or a combination. And then I think, well, it has to form a word, so permutation is going to be selected because order does matter. I have 26, picking 6. Going on to number 13. 6 letters with repetition allowed are selected from the alphabet. What is the probability that none of them is the vowel A, E, I, O, U? Repetition is allowed. Okay, so first of all, and the denominator is still the same, 26 to the 6. Repetition is allowed. That means I'm using everything except A, E, I, O, U, so that would be 21 to the 6. Number 14. What is the probability that in a group of 6 people, at least 2 were born in the same month? That means I could have 2 people born the same month, or 3 or 4. It gets to be a lot. So I'm going to do 1 minus everybody having their own assigned birthday month. So again, every person that is born has 12 months to possibly be born in, so that would be 12 to the 6th. If everybody is assigned to a different month, that's a permutation because we're assigning a month, and that would be 12 months, picking 6. Okay, now I'm going to skip down to the birthday problem because these are really fun. Number 16, here's the famous birthday problem. If I have 10 people in a group, what is the probability that in a group of 10 people, at least 2 have the same birthday? And again, I'm going to do the same thing. 1 minus everybody assigned a separate birthday. There are 365 days in a year, so I'm going to raise it to the 10th power because I have a group of 10. So in the numerator, I want everybody to have a different birthday. If I take away everybody having a different birthday, what we'll have left is people that will have shared birthdays. So my permutation is 365 choosing 10 because that's assigning 10 different people to a different birthday because no repetition is allowed in permutations. And you can figure out what that probability is, and I'll just give it to you. It's 0.117. Now, if we increase that to a group of 30, it's the same concept. Permutation of 365 choosing 30 all over 365 to the 30th power. And again, notice it's just assigning 30 different people in the numerator to a different birthday. That's what that numerator means. Permutation 365, choosing 30. The denominator means everybody who is born has 365 days to choose to be born. So that's my sample space. Now notice this gets up to 0.706 as that probability. Actually, if you have 23 people in the room, you have a 50% chance of sharing a birthday with somebody else in that room, or two people would share a birthday. And that's always just kind of a fun fact. A fun little thing to kind of investigate. Number 15, let's go back and do 15 and then we're going to be done here. It says 3 cards are selected at random from a deck of 52 cards. What is the probability that all 3 are spades? So in the numerator, I'm just saying, okay, what is the probability of all 3 is spades? Does it matter in the order that I get my cards? And the answer is no, it doesn't matter. So I'm going to put a combination of 13, because there are 13 spades in my deck, picking 3. And in my denominator, it's just picking 3 cards. How many ways can I pick 3 cards out of my total deck? And that would be 52 choosing 3. Okay, there we go. That is all of the notes for section 7.3 in finite math.